Next type of positive displacement pump we'll be discussing is known as a metering pump, also called a dosing pump, a controlled volume pump, or a proportioning pump, amongst other names. This is a typical design of a metering pump. Most are run by electric motors, although there are some air-driven ones, and they consist primarily of the motor, the gearbox, the head of the pump, the liquid head, and discharge and inlet valve balls. And unique to this type of pump is generally a method to change the stroke length of the pump. Some of them also have the ability to change the stroke speed. The stroke length is called the turn down ratio, or it refers to turn down ratio, so that you can go from virtually no flow to the maximum flow capability of the pump, which is very important when you're doing metering or deciding what kind of pressure and liquid level you're trying to attain. The diagram here shows a single chamber or single piston metering pump. There are metering pumps, as with air diaphragm pumps, that have multiple chambers to them, but by far the most common type of metering pump is the single discharge or single head, single piston metering pump.
Okay, let's look at this curve of a metering pump. This is a single diaphragm metering pump, and as you can see, the pressure rises very sharply, very quickly, and then falls very quickly, and then you have this dead space here where nothing's happening. Well, nothing's happening on the discharge side. This is when the pump is drawing fluid in through the inlet and filling the chamber. And then as soon as it's full, of course, then it goes through the discharge cycle. It is much more radical than what we saw on the graph of an air-operated diaphragm pump. There's a couple reasons for that. One is that the metering pump is electric, and it's going through a gearbox and is running at a constant rate. So many cycles per second based on, whatever the electricity it has, and it wants to stay at that speed. So if you increase the back pressure, it still is putting out pretty much the same amount of fluid until it gets to, if it has a relief valve, it'll relieve its pressure, but that'll be the peak. But otherwise, it wants to produce, it's going to produce that same volume. So you get this huge spike. You also notice that it's much smoother than what we had on the air-operated diaphragm pump. You don't have those big spikes that we have on the other one. This is a much smaller pump than the other one. That probably has something to do with that. And also, it's good to note that the air-operated diaphragm pump is working off of air pressure. So the back pressure in the system determines the rate of the pump, and the airline pressure. So if you increase your air pressure, the pump will run faster. And if you increase your line pressure, or the system pressure, the pump slows down. Very different from the metering pump, and it's something to keep in mind when you're designing your system.
So why is a metering pump used? Well, primarily to meter or dose a precise, repeatable amount of liquid into some other system. They're used for blending, they're used for injecting chemicals into another chemical stream, for example. Any application in which it's important to make sure the flow is consistent. The advantage, as I said before, is its flow and pressure repeatability. The flow rate is controlled by the stroke length, which is variable, and often the speed, which can be varied. And as David mentioned, because it has this consistent repeatability stroke speed and stroke length, you get a very accurate flow. However, because it's a positive displacement pump, remember that the flow is going to be non-steady. Over a given time period, the flow amount will repeat and be consistent. But during the shifting process where we capture liquid and expel it out the discharge, we have, as Dave explained, these high peaks of pressure and very low points where there's no flow at all. Now, that's where a pulsation dampener can play an important part in the application of metering pumps, because as we've seen already, when the dampener is installed properly at the discharge of the pump, it will accumulate liquid, generally more than the stroke volume, so that when the valley of the pressure and flow period occurs, the dampener will release some of its accumulated liquid into the flow stream, filling that void where the liquid stops and the pressure drops. And then you will have a more accurate and repeatable flow and pressure. It's important because it's difficult to measure non-steady flow. And many of these applications are involved with some sort of a flow meter, which requires generally the pressure and the flow to stay within 1.5 to 2.5% in order to properly meter the flow rate. They're used generally for clear liquids. They don't really handle slurries well, more clean liquid type pump. And also, because most of them are single diaphragm pumps, they need some assistance in closing the valves, particularly the discharge valve. So what's known as a back pressure valve is generally installed in the system to create some back pressure, which helps to close the discharge valve ball between its discharge and inlet or suction stroke. That back pressure valve would be installed downstream from any pulsation dampener installed in the system. And with the back pressure valve, it's very important to have an inlet, or a discharge dampener, because if you have inconsistent flow and pressure going to the back pressure valve, it's going to be constantly opening and closing and trying to adjust to the pressure change. With the dampener installed, the pressure to the back pressure valve and the flow to the back pressure valve is near linear, and the valve will operate properly. Another drawback for a metering type pump is that they're generally, even though they're positive displacements, very limited in their suction lift capabilities. They almost need a flooded suction, but they'd have some capability. An inlet stabilizer installed at the inlet of the pump can help accumulate liquid during the inlet stroke and minimize, in many cases, the work that the pump has to do, protect the system, and make sure that the chamber gets completely filled on the inlet stroke. In other words, to help minimize cavitation problems.
So here's our system, our metering pump system again. This is the undampened curve, and this is, we've added a dampener, and that's the curve of that. Again, we have not changed the back pressure valve or the speed of the pump. It's running at the same rate. And you can see there's a huge difference. Of course, this is very, very flat. We have a plus or minus, was it 1.2 psi with the dampener. And here we've got about 12 psi all the way up to 86 psi. It's a huge range. Now, when you're sizing this system, if metering is really, really important, you don't want to get too big because the dampener holds fluid, and so you can vary what's coming off the discharge a little bit. So sizing is important. If you look at this, you'll see this little section here and the same one repeated over here and here. You can see they're at the same rate as the other curve. This is probably caused from the valve closing and opening. Produces a little bit of noise in the system. There is a length of pipe between, or a distance of fluid between that ball and the dampener, and that is accelerating and decelerating. But very flat curve, and that's generally what we want to see. This is much flatter than the curve that we had on the air-operated diaphragm pump, and this is much more radical. So obviously the way that was handled is the dampener has a larger gas charge in it than the dampener that was on the air-operated diaphragm pump. So that the ratio of the amount of fluid that's coming out from a single pulse is different when when you compare this one to the air-operated diaphragm pump. The bigger the diaphragm relative to the amount of fluid per pulse, the flatter the curve. And generally, air-operated diaphragm pumps, a little more fluctuation is totally acceptable. In a metering pump, often they're measuring the flow, and to measure flow accurately, you want the flow to be very steady. Again, if you make it too big, it can store quite a bit of fluid, and so you can, if you have any valves opening or closing, you can get a variation in the flow.
The third type of pump we're going to discuss is the peristaltic or hose pump. Peristaltic gets its name by the pumping action created by the design of the pump. Typical peristaltic or hose pump consists of a case, and not seen is a motor on the other side of a shaft connecting this wheel, which drives shoes or rollers. As the rollers come around, they compress the tube, capturing liquid and pushing it forward out the discharge. When the roller or shoe passes the inlet, it opens up, creating a draw or a low suction area which pulls liquid in. That liquid is then pushed around and out the discharge. There are different designs in the sense that some of these wheels will have 1, 2, 3, or 4 different shoes or rollers on them. Those rollers, the number of rollers, can impact the pressure that's generated. They can impact the life of the hose and various other factors. The amount of solids that can be handled, the viscosity sometimes can be affected by the number of shoes in the pump.
All right, here's the pressure curve off of a 2.5-inch hose pump, one that we've got in our lab. And it is undampened, of course. And as you can see, it is very radical. It is the most radical one we've looked at so far. It's very sharp at the top and goes down to nearly ambient pressure. With the hose pump, the flow will actually reverse after the shoe passes the discharge, and makes it more radical, and the dampener has to be sized bigger. If you look at this, it is not a sine wave. It is somewhat sinusoidal, but it's very, very sharp, kind of like a sawtooth. The metering pump, the curve was steep, but it was pretty much a sine wave.
So just like the air-operated double diaphragm pump and the metering pump, peristaltic or hose pumps have several advantages. One of them being, since it's a hose, there are no valves and there are no seals. The flow simply stays in contact only with the inner part of the hose. At both ends is connected to the discharge, and the case never touches the liquid, unless there's a failure of the hose, of course, and there are means to protect that. There are leak detector devices and just good maintenance policies. But the hose can be therefore made of any material that is chemically resistant to the product being pumped. The case, the shell, can simply be made from a mild steel, some cases of plastic. It's the same as the shoes and the inner wheel. Those do not have to be chemically compatible with the product being pumped. Another big advantage of the peristaltic hose pump is that it is the simplest of operating mechanisms of most any type of pump. It's simply a hose. There are no valves, no seals, nothing has to open or close. It's just a simple matter of the shoes passing over and squeezing and releasing the hose to generate the pumping action. It's a positive displacement pump, even though it's rotary. It has very good slurry handling capabilities, very good abrasive handling abilities, and it handles relatively good size solids, although depending on the discharge pressure and the amount of squeeze the shoe imparts onto the hose, it can reduce hose life. Being positive displacement, it has very good self-priming capabilities. Can be very important in a lot of applications because it's used a lot in mines, and it's used a lot in wastewater treatment. That's also because it's a simple operation type pump, very simple to maintain. And hose changes, at least in the newer designs, are quite simple. It's simply a matter of disconnecting the hose from the inlet piping and the discharge piping, turning on the pump, and the hose feeds right out through the discharge, and then a new hose is fed right into the inlet and it pulls it around. Other than that, there's really almost no maintenance at all. It's a very simple, workable design and is becoming more and more popular in many, many applications. Metering with the smaller sizes, I mentioned it earlier, with using tubes has become quite a big market for this type of pump because it does have repeatable flow, but it also has a pulsing flow. So when used for metering, they typically will need to install pulsation dampener at the discharge. The larger sizes with reinforced hoses are used in mining, in a lot of dewatering applications, pumping abrasives, slurries, a lot of paint, sludges, and general chemical transfer. Because again, of its simple design and because only the tube or the hose itself comes in contact with the liquid. There are even now some hoses that are being designed with an inner liner that only the liner of the hose is chemically inert to the product being pumped. It does have very high suction lift characteristics, very similar to those of an air-operated double diaphragm pump, and doesn't necessarily have to have the hose wetted to create its high suction lift capabilities like an air diaphragm pump does. Another application that's a big part of a hose pump is in the sterile or hygienic market, used to manufacture a lot of vaccines and other components, and it is, as I mentioned before, in a heart-lung machine. Again, because it's a simple design and because the liquid only touches the inner surface area of the hose. Sludge and slurries we already talked a bit about, but it handles high viscosity liquids like an air-operated diaphragm pump, and it handles abrasive slurries quite well. So, like the other pumps, every pump is not the solve-all, save-all of every application. So what are the drawbacks for peristaltic pumps? Well, they have a very significant pressure and flow variation discharge curve, especially in the single shoe design. The more shoes, the smaller the pressure variation between strokes or shoes, if you will, but they're still going to be there. Obvious way to solve these problems where it's necessary is to install a pulsation dampener at the discharge of the pump, and the inlet side of a peristaltic pump has some particular characteristics as well, which we can talk a little bit later about, or Dave will mention, because of the shoe coming past and, if you will, popping open the hose, we get some pushback in that inlet area to the pump. So an inlet stabilizer is often required in many of the applications for a peristaltic pump. Another drawback is, again, depending upon discharge pressure, slurries, abrasions, hose life is a definite consideration for this type pump. Even though it's relatively easy to change in this day, it's the limiting factor in the maintenance required for this type of pump. So it's very important to make sure that you have the proper type of hose for the chemical or material that's being pumped. Peristaltic pumps run by an electric motor cannot be stalled. You must use some sort of a bypass or big pressure relief type of valve if you are going to try and close the discharge. So they are constantly running pumps. They're not variable speed unless a VFD drive is added to the motor. So pretty much constant speed and pressure type of discharge. And at this point, no one has been able to figure out how to make a PTFE tube that will withstand the repeated crushings and expansions, and so it's limited in handling some of the most nasty, aggressive chemicals.
Here is the curve again of the undampened hose pump, the discharge from the undampened hose pump. And here we've added the dampener, and that's what the curve looks like there. This particular hose pump is a 2-shoe pump, so this would be the discharge from one shoe, and then there's the dead zone, and then the discharge from the next shoe. When dealing with the sizing, a lot of times they will give the pump flow in a per revolution. For your sizing concerns, if it's a 2-shoe, you divide the flow by 2. If it's a 1-shoe, then of course it would just be 1 pulse per revolution. Because, as we mentioned before, of the sharp nature of this curve, in this case we have a total of 82.3 psi variation between the top and the bottom. Very high. After we've installed the dampener, we're getting a plus or minus 3.5 psi, which is pretty good in most applications. If you wanted less than that, then again we need a bigger dampener. We're getting a little bit of noise in there, of course, from the system dynamics. The inlet side also has the same situation like an air-operated diaphragm pump. We don't have a curve of that, but it's a similar type of thing. If you have a long inlet, the hose when the shoe passes the hose has to, or wants to go back to a round shape. That's what sucks the fluid back into the hose. And if there's a long distance, it can have a hard time doing that. You won't get as good a flow rate. It will help significantly in some cases to have the inlet stabilizer and a pulsation dampener on the outlet. On behalf of Gary and myself and Blacoh University, thank you for watching, and we hope that the information can be useful to you and company and whatever application that you're working on.